Hello everyone. In this session, let us see the switching characteristics and switching model of a power Mosfet. Before we analyze the switching characteristics of the power Mosfet, it is very important to draw the equivalent model or the switching model of the Mosfet. So in this diagram, you can observe that we have a enhancement type Mosfet which is represented, and there is a parasitic capacitance CGD, CGS and CDS. CGD is the parasitic capacitance between gate and drain. CGS is the parasitic capacitance between gate and source. CDS is the parasitic capacitance between the drain and source. And you can observe a NPN transistor and a resistance which is represented across the base and emitter. This is an NPN transistor. Why we have to represent an NPN transistor here? That is because if we don't apply a gate signal to the Mosfet, what will happen to the enhancement type Mosfet? Mosfet is off, right? It is nothing but it appears like this. See, if we have a Mosfet, this is a rough sketch. This is the body or the substrate. If it is a N type, means our substrate is P, and we have drain and source. So you don't have any gate signal which is applied. Okay, the gate signal is not applied. So what is this one now? This is an ENPN transistor. So we have an NPN transistor which is represented along with this resistance. This is called as bulk resistance. Okay, it is a bulk resistance. So this bulk resistance is actually very small. It is actually very small. So instead of representing this NPN transistor along with this bulk resistance, we represent it by a diode. So all the Mosfet in parallel with an internal diode. Okay, this is the equivalent model. So we can represent the switching model like this. We have the gate terminal, we have drain terminal and source terminal. First represent all the parasitic capacitance. This is between gate and drain, between gate and source, between drain and source. Once you draw this, we have this internal resistance, that is RDS, between the drain and source terminal, and this is the current which is represented in terms of its transconductance. This is actually the switching model of Mosfet. Switching model of a Mosfet. So unlike your BJT, the Mosfet doesn't have a secondary breakdown phenomenon, and you don't have the concept of charge storage in the case of Mosfet. So you know it is a voltage control device. So how our switching characteristics looks like? So when you apply a gate voltage of magnitude V1, what happens to the gate to source voltage? This is source, this is the source, this is the substrate, this is the drain. Drain, substrate and source. Okay, this is the gate. So you apply a gate voltage of magnitude V1. So what will happen to the capacitance here, which is between G and S, CGS? So the parasitic capacitance gets charged. So that is what is shown here. So the capacitance gets charged, nothing but VGS will increase and it finally reaches a value V1. That is nothing but what is applied. And in case it will remain at V1, and what will happen if the input is removed, gate signal is removed, the capacitance starts discharging and becomes 0. And remember, all these capacitances are the parasitic capacitance. It is not the physical capacitance which you are going to connect. It is just imaginary thing. So here when the gate to source voltage increases, obviously the drain current will also increase. You don't have a storage time here. If you look, you don't have the storage time. So the delay time during turn on is nothing but the time required for the channel to form. So once your gate voltage reaches the threshold voltage or your pinch off voltage, the channel is formed. So that duration is called as delay time during on, and the time from the threshold up to the 90% of this V1, okay, 90% of this V1, you call it as a rise time. And from the from this 100% to 90% drop down is the delay during turn off, and around 90% to almost 0, it is the off time. So this entire time duration TD on plus TR is your on time of the MOSFET, and TD off plus TF is nothing but off time of the MOSFET. So you don't have this charge storage concept in the case of power MOSFET as compared to the power BJT. So you can observe that your on time and off time is very less, so that you can achieve a higher switching speed. So always your MOSFETs are having a higher switching speed compared to that of the BJT. So this is all about the switching model and switching characteristics of the power MOSFET.